Hey everyone, and thank you for tuning into this talk. We've got a lot of exciting content packed in here, and we're going to try to get through it as quickly as possible. In particular, we're going to be talking a little bit about machine learning and how you can build a generalizable end-to-end machine learning solution to leverage your existing data for detecting abuse and cheaters in your games. We're going to use Amazon SageMaker to do this, and before we get started, my name is Nick Walsh, and I'm a developer advocate here at Amazon Web Services. So let's give a quick run of show for what we're going to be talking about today. First, we're going to talk a little bit of background on cheating, abuse, and sort of the landscape around all of those nasty things that we want to be able to detect. Next, we'll talk about some of the current methods for being able to perform this detection and remediation. We'll cover a little bit about machine learning. Again, you don't need to be an expert or have any expertise or experience with machine learning to be able to enjoy and be able to make some of the things actionable from today's talk. Next, I'll discuss what it actually means to build a pipeline using relevant cloud services to be able to go from the data that's being produced live on your game servers to a deployed endpoint that serves production inferences. And then lastly, we'll talk a little bit about the next steps. Once you've deployed your application, how can you go past 0 to 1 and onto a more scalable or cost-effective implementation? Lots to cover, so let's get right into it. First, when we're talking about the landscape of abuse here, we have everything from cheating, abuse, and a lot of things in between. When it really comes down to it, there's a lot of different forms of this that exist, and this sort of variety and the variability in the very things we're trying to detect inherently makes it a difficult problem to solve. We also see that a lot of the behaviors that we can see objectively and measurably are not always telling the full story. There are concepts like intent of the player that can become very critical in how we as game developers want to take action against a player. It's one thing for someone to be a victim of a bug that caused them to fly. We wouldn't necessarily want to punish them, but someone who's abusing a bug to be able to gain advantages in a game or to abuse other players, well, this is something we would definitely want to be able to take action from. So at the end of the day, again, the data doesn't always tell the full story. We typically want to be able to service this activity because it can be correlated, but we don't want to always say that it may be causal. But, you know, more than anything, cheating and abuse and even bugs are just anti-fun at their root. And anytime we have some sort of situation in our game that fits under any of these categories, game developers and players alike want this to be able to be snuffed out and identified and resolved in the long term. You know, there are some tangible impacts here around players probably playing your game less, players giving bad press and media about your game. But at the end of the day, we all want the same thing. Players want to be able to play a fun game, and game developers want to put the best game forward that they can. So when we're talking about cheating and abuse, there's a whole sort of variety of ways that this happens in the status quo, and here are just some of the most popular forms of abuse that have existed in various popular game genres. We see in games like real-time strategy games, things like removing the fog of war. Again, an element that's critical to obfuscating information, but when one side can remove that, they gain a significant advantage. In first-person or even third-person shooters, we see sort of the classic aim bots or wall hacks to be able to see through walls. Again, this trend of being able to access information and display that in a game where imperfect information is part of the decision-making process becomes a very consistent sort of vector for abuse for how certain players try to gain an advantage. Additionally, in any game that has an inventory or a trading or a monetary exchange system, you know, MMORPGs are a great example here. Duplication of items in abusive ways can completely dismantle or devalue currency in the in-game economies that exist here. So it's really important to prevent the duplication of items or the duplication of items so that this doesn't happen in your game. And then lastly, there are even some, you know, less insidious examples like texture modification. By swapping out a single file, oftentimes people can change the way certain entities look in their game to be able to gain a visual advantage. Here I have an example down the bottom where even without modifying texture files, sometimes just changing the graphics settings in a game can cause a player to have a different advantage. So all of these, regardless of how insidious our players are things we want to sort of avoid being possible. And so a lot of those things I mentioned there were all sort of very intentful, very deliberate. They rarely are going to happen on accident. Players are seeking out ways to abuse code to be able to gain these advantages. But what we find here is that those very same parts of the code that enable those cheats to be possible oftentimes enable sort of accidental scenarios here where players not only don't gain advantages but can become victims. Falling through the world is something that can happen in any sort of game where you have a landscape and a mesh and you happen to just walk up against this hill the wrong way and you fall through the world, and that has happened in many games before. This player probably dies, maybe they get access to part of the map you didn't intend, but ultimately this wasn't intentful. Similarly, if you load into a match and you can't see certain things and that prevents you from being able to fight your enemies, that's obviously not a fun experience either. You can get stuck in a wall, not great. And lastly, you may have tried to buy an item and it could have charged you more than you expected. You start to see that a lot of these bugs here are sort of the flip side of the coin to some of the abuse vectors that I mentioned before that cheaters use all the time. And this is where it becomes tough to build automatable systems that detect sort of from the objective data, is this someone who's trying to abuse our system, or is this someone who's simply sort of a victim to a bug? And this sort of landscape, I've said the word landscape a lot of times, but it really plays out as a spectrum here. You have the extent to the impact of a bug or an effect, either low impact or high effect, or everywhere in between, as well as the intent. There are some folks that completely stumble into certain bugs or can either, whether they're beneficiaries or victims. And on the opposite end of the spectrum, there are folks that may completely try to decompile the code from your game to seek out these bugs and use those bugs for personal gain or for the harming of others. And we see that, I have a handful of example points here that fall under discrete common categories and buckets. But in all honesty, you could probably fill out this entire spectrum. And there's another axis that I didn't even include on here, but you could if you were trying to figure out what was most important for figuring out in your game, which would also be, whether someone was benefiting or losing from a given sort of scenario, right? So if it's not just impact, like is it positive or negative, or amount of players that it could impact, but I guess that falls under the impact category. Essentially, it's not clear. There's no really discrete way to bucket a lot of these bugs, so we do want to deal with the most malicious and highest impact bugs broadly, and we sort of work backwards from that sort of ordered priority list to be able to make sure that we can detect cheaters and abusers, and maybe even bugs along the way as well if they fall into the high impact category. Okay, so current methods, there are quite a few of them. Much like in many sort of systems, the more that game developers talk about them, the easier it is for folks to get around to them. So I'm going to talk more about generalized trends here than any specific individual implementation, as a lot of these have also changed over time. A lot of methods work well, but once they're figured out, the sort of game of cat and mouse goes on. So first we'll start with client-side detection methodologies. So in any sort of architecture where you have individual game clients for players with some sort of maybe either direct peer-to-peer connection or a connection to a master game server, there are ways to have your game client decide on the client side whether the player is trying to be insidious or not, or doing things that they shouldn't be. Examples of this being running scans on processes and sending MD5 hashes back to maybe the authoritative game server, or if there isn't an authoritative game server, some other sort of process that's going to perform some sort of check against a known set of insidious MD5 hashes. So if the hashes from the process in your system match any of the ones that they know to be evil, then they will perform some sort of action based on that. This is not unlike the way many antivirus systems can work on your PC. Now, this is sort of the low bar. We want to be able to test known entities that are running on your PC against other proven known entities that are, already determined to be cheating. So this works really well, but the other thing we have to understand is you can't always trust the data that's being sent from the client, and I'll get into this in just a moment. But ultimately, actions are going to be taken based on the interpretation and the matching of this hash. Now, the level in which you take the invasiveness is going to be determined by, the preferences that your players have and you as a game studio choose to add. You can have everything from simply scanning what a typical application may have access and privileges to a kernel level driver essentially that can start from boot up to ensure that anything downstream can be captured to perform this comparison. Further, you can do things like reading local memory or disk space. Again, the more invasive or the more comprehensive sort of the surface area you want to consume, the more data points you'll have. But it makes it tougher, but all the while not impossible to hack. And all of this is caveated with the fact that we still can never really trust the client, right? Unless you're making those authoritative actions directly on the client, and even then, point being the data that your application is receiving or that the client is sending up to the server that will perform some of these checks, there are very few sort of ways that we can guarantee that that data has not been spoofed, replaced, or completely substituted in to prevent the player from being caught. Okay, so this sort of brings us around the other way. If we can't control the data that's being sent or trust in the entirety the data that's being sent from the client to the server, well, the server represents the golden source of truth. So what can we do on the server side where the game state is running in a multiplayer game scenario or an always online scenario to be able to sort of get around this fault of untrusted client data? Well, you can define some sort of arbitrary policy definition. So think about in a MMORPG or in a first-person shooter game. You know a bit of information because you've designed the game so that you can work from first principles to say, okay, if this is the movable speed that a player can have and they can reach this X maximum speed, if their speed is ever over X, then perform Y action because they're likely cheating. So in a scenario where, again, you've designed the game, you understand the mechanics by which it can work, you can take that knowledge to craft an arbitrary policy. Now, this can work. However, there are a few drawbacks to this. First being that it's brittle. Over time, as you make changes to your game, the first principles may change, but if these first principles are dynamically generating your rules, then you will run into a scenario where either you launch your next patch and then lots of players are being flagged by this anti-cheat unnecessarily, false positives, or you are continuously spending a lot of engineering resources to recraft and recreate some of these policies. Now, in a scenario where we're talking about something very simple like move speed in a game that doesn't have a lot of move speed modifiers, this may start to be a really easy way to get off the ground. But what we find is there's a lot of scenarios that you may not have thought of. For example, you may not think of the falling speed of a player who accelerates off of a tall building as a part of their movement speed. However, if this is something that happens, a totally innocuous behavior, your system may flag them for cheating. Even without a change to a game mechanic, introducing a new map with a tall building could easily break this sort of model. So we want to avoid these manually crafted policies wherever possible, even if they are really good for catching the most obvious cheaters or surfacing them at least in the beginning. Ultimately, time and brittleness are the biggest drawbacks there. Now we have sort of an approach from the other direction on the server side, and this is going to use more fundamental statistical methods. We can call this unsupervised machine learning or anomaly detection, what have you, but ultimately this is going to be looking at intrinsic trends in the data without sort of introducing known biases that we have as game developers to be able to look at the statistical outliers out of the pool of behavior that exists in our game. So an example here would be for a given pool of players, for all of move speeds across all games for all players, are there very particular instances at the tail end, on the high tail end, that we can find here? And if we surface that very small subset of players or actions or games, can we look at that and then work backwards to say, okay, this behavior that we noticed from this outlier seems insidious or wrong or is a bug, so we will then investigate that. Again, we're trying to reduce sort of the brute force approach of looking at every player in every game. So if we take the statistical outlier there, it enables us to do that. But again, this doesn't imply causality. This also doesn't imply that there is even a bug or something insidious to begin with. Depending on the statistical trend, even some bad or bug-based behaviors may not be mapped directly to existing metrics that you're already measuring, so they may not even be surfaced. But ultimately, things like anomaly detection or statistical outliers and the systems that we can build around this on the server side can help us to more quickly surface these edge cases for either detecting or investigating whether they're cheating or whether this could be abuse or neither. Ultimately, authoritative servers are great. We know that we can trust the data because as a game developer, we run that and manage that. But surely there can be a better methodology, right? Can we dynamically sort of generate rules in a way where we're also leveraging the raw player data? Can we sort of marry the two classes together, or the benefits of them? And this is where machine learning is going to come in particular supervised learning. So in a supervised learning scenario, this is where a system learns from a data set to distinguish between a handful of different classes based on labeled data that's fed to it. So for example here, if we loaded in telemetry data to extend the MMORPG movement example of a large number of examples of movement data for players that are not cheating or not exhibiting bugs, and a large set of telemetry data that includes data for players that has been cheating or using bugs. It is the task of the machine learning algorithm to be able to differentiate between these two classes when given a new piece of unlabeled data. Now, all of the data that's fed in needs these labels, and that's how the machine learning algorithm will actually determine what these rules are. This has a lot of benefits to the game developer, but one of the most important ones is that this model is custom to your game's data. So while the algorithm can be something that can be interchanged for lots of different problem statements, it's the combination of using that algorithm with your data to be able to produce a model that will achieve the outcome that you most want. And broadly, the big two value propositions here are A, that it's automatable. By feeding in the data to a given algorithm, the model will be able to then serve new inferences in production. And lastly, it's granular, so you can conditionally take actions based on the confidence value of these inferences. If you have a certain threshold for an extremely confident prediction, you can automatically take action based on that. And conversely, if there's not a very high confidence at all in a certain prediction, you can either not surface it to anybody, or in the immediate zone, you can escalate this to an account manager, for example. Okay, so I promised before that you wouldn't need any machine learning experience for today's talk, so I'm going to cover it as quickly as possible for the context of games in about 10 minutes. First, what is machine learning? I hinted at this a little bit before, but ultimately machine learning is a process by which a system will make decisions based on rules that it has learned on its own. So two main components there. First, automated decision making. Once the system has developed its rules, it will be able to take conditional actions in the future. That's going to be the inference and the prediction side. And then the first part, learning on its own, is going to be the training aspect that will be using machine learning algorithms. So for supervised learning, there's three main parts. First is coming up with your problem statement, figuring out what you want to solve. Second is the training process with that labeled data. Again, unlabeled data can be used in an unsupervised learning scenario where we're trying to learn intrinsic aspects of the data as opposed to injecting sort of our biases about what that data may mean. And then lastly, we're going to have inference, where we can use that model that we created in step 2 from our training, and we can feed it new data to perform inferences on new data. Okay, so step 1. We have a problem, we need to ask ourselves, what are we trying to solve for? In the example that we're posing in today's talk for a supervised learning scenario, we want to be able to classify between two classes of players, cheaters or non-cheaters. You can substitute these as well for abusers or non-abusers, or people that are affected by bugs and people that are not affected by bugs, so on and so forth. In machine learning, we're going to be calling these classes. They're two unique sets of the population that we want our algorithm to be able to distinguish between. Now we're going to talk about training. So I'm going to give you an analogy and run with me here. I promise by the end it'll make a lot more sense. We're going to think about the life cycle of toast. So when we think about toast, we have a handful of key entities that exist from the sort of birth of the key primary ingredients to the end result that we want. So first we have sort of the primary ingredient, wheat. This then has a few processes by which it undergoes before it becomes toast. Going through those quickly, it's processed from this raw material to this more usable material, grain. And then it undergoes a transformative process in baking to become bread. And then lastly, the last step that we all take will be putting that in some sort of toaster, and at the end we get toast. Now, you're probably wondering, what does this have to do with machine learning? Well, for each of these key entities, there's sort of these discrete elements that are all the result of these individual processes that come before them. We understand this, and when we all think about toast, we may not all grow our own wheat or buy our own grain, but we do have an understanding of how the decisions that are made and how those processes occur can affect the products that we have. Now, when we think about this in the context of machine learning, actually, it's not quite different at all. So we start with the raw data. This is actually rather like whereas wheat comes out of the ground, the raw data is produced by your game server or by your player's clients. Essentially, the system of records of all of the actions that are taken exists somewhere. And note, while those are probably powering some game servers or some other logs that your application is running, those are typically going to need to be pre-processed into some sort of cleaned version of data. This can be everything from just taking out some of the values that we don't need or changing some of the formats of the data. Now, this can be ultimately transformed into engineered features. Now, this is pretty unique to machine learning and doesn't exist in most common other ETL tasks. Engineered features are going to be unique permutations and custom crafted data points, essentially, so that for a given data point, it may have a feature that when we look at our data set, we want to say, okay, well, these two combinations of factors can help us to describe why maybe this case will be a cheater, whereas this other case may not be a cheater. We don't need to ascribe exactly why. The machine learning algorithm will figure that out on its own. But we need to be able to codify these features that we think of subjectively with data such that the machine learning algorithm can figure out how to differentiate between the classes. Now, once we have these engineered features, we will be able to train our model. Now, I'm going to walk through each of these step by step. I know this is a lot at first glance, but we'll break it down. So first we have the raw data. If we're thinking about something like telemetry around players' movement in maybe an MMORPG, for example, or a first-person shooter game, you have position in both the X, Y, and Z axis, you have the date for the timestamp of that packet that's sent, and maybe if there was a specific type of action that was taken. Now, the game server clients are constantly sending these packets to the game server is reconciling those with the latency of all of the players, and for each tick on your game server's event loop, it will have one of these data points for every player, most likely. We see on the left-hand side on a typical EC2 virtualized instance on AWS, you may have sort of just a slew of play logs as JSON files, and if we were to open one of those up, it'll give us something that looks like the right-hand side. A sequence of individual events on a player-by-player basis, sort of until the end of time or for as long as the server needs to hold on to that information. Typically this will be offloaded elsewhere, so cleaning may exist in other pipelines that may not be machine learning oriented, but we'll have very particular things that we're looking to clean the data for our use case. So that's where this starts to come into play, cleaning our data and engineering our features. So whereas the game server produces a specific data structure or data type because that's going to be ideal for the game server, we may want this to be in a different format and may want to include or exclude certain features here for our machine learning scenario that we may not need, that may not exist elsewhere, and again, excluding some that may not be relevant here for our machine learning example. So examples of parts of this processing include removing duplicated entries or incomplete entries for whatever reason, changing the data type. So for example, if our machine learning algorithm requires a double instead of a string for a numerical representation, we'll want to perform that transformation here. And then lastly, engineering features, typically referred to as feature engineering. We're going to want to create these sort of composite dynamic features that will help us, hopefully, to display the characteristics of a class. So for example, before I spoke about the raw data from the game server having the past X position and the current X position, and the same for the Y and the Z directions, here we've simply cut those out and created these new composite features like position X delta, position Y delta, position Z delta, speed XY versus speed in the Z direction. These are custom features that, due to our intuition or even sometimes guessing, will hopefully be able to help the machine learning algorithm differentiate between the two classes. Again, feature engineering broadly wants to take these factors that we consider from often a subjective point of view that we understand about our player base and our game, and we want to codify them and make them quantitative. And lastly, this is sort of where a lot of the magic happens. I know people think of machine learning training like a black box, but it's much more straightforward than that. Let's think about the toaster example again. So when creating toast, you want to toast that, and this process starts with bread as an input. You put it into this black box, a toaster, whatever your favorite brand is, and we want to get toast as our output. But notice on the toaster, there's actually a few knobs and dials that we can modulate. We have some options here. You can probably set the temperature, the duration for which it'll toast for. Maybe you have a very advanced toaster and you can alter the number of coils that end up heating up, or the heat cycle type if there's something along those lines. And we see that, the quality of the toast that comes out is not just a factor of the bread that we put in, but it's a combination of the input bread with all of the different settings that we tuned. So intuitively, if we use a higher temperature and control for all of the other factors, it will probably come out more toasty or darker. If we keep it in longer, probably a similar extent, and so on and so forth. But the point being that the resulting output is a unique result of the permutation of all of these different knobs that we've tuned to any of their respective values, as well as the bread that we've given on the input. Now, where am I going with this? Well, when we relate this back to a machine learning pipeline, specifically for our game example, we can see that in supervised learning, it's very, very similar. So we start with our engineered features, and we can just call this data as our input. And everyone wants to have a model as their output. They want to be able to have this decision boundary and a system that can decide between multiple classes. And we will get there. But to understand how we get there, we start to look at this sort of box in the middle. And instead of a toaster, it's a machine learning algorithm. With this machine learning algorithm, and there are many, all of which have their own pros, cons, and strengths and weaknesses, which I'll get into in a little bit. But ultimately, this is, again, think of this like a device or a process by which we give an input and it will result in an output. Now, for a given set of input data, the model that you get on the output will not always be identical, and this is due to differences in something called hyperparameters. So just like in the toaster, where there were a lot of knobs that we could tune to affect the process by which the same piece of bread undergoes when put into the device, these hyperparameters are essentially those knobs for how the algorithm is going to perform its processing on your data. Now, each algorithm, think of them like a different brand of toaster. Each brand of toaster may have its own different types of settings and knobs that you can tune on it, and algorithms are the same here. Because each algorithm fundamentally operates differently under the hood, these hyperparameters are going to be things like the number of epochs or the maximum tree depth in a random forest classifier algorithm, maximum number of features, minimum sample split. These are all things that will affect the process by which model training happens. Changes to some of these factors can do things like increasing the amount of time it takes to train the model to a given level of accuracy, things like affecting exactly how many splits are going to be happening up and down the tree, or the maximum number of leaves that you can have in a random forest example. Again, the large selection of which ML algorithm you choose is often a difficult problem, and that's one that we won't get into today. But again, the word hyperparameters comes up a lot, and I wanted you to understand exactly how it fits in here. So as a result of this entire process, we do get our model output. And to sort of recap here, this is all the context of training machine learning models. So going from your pre-existing labeled data to a model that can then try to serve inferences on live data. We'll get into inference right now. So you want to use your model, you want to perform inferences on live data, because that's how your machine learning experiments actually provide business value to your organization. It's great to have this hypothetical math equation, but you really want to be able to make this actionable. So with our data, we can create a model from this, and by feeding the data into that model, the live data, we can get these predictions at the end. The model is essentially a math equation, and it's a set of rules. It's not this actionable piece of code on its own, and you often need to use the libraries that actually, the software libraries that built that model to be able to create actionable inference code. So what does this actually look like in practice for performing inferences? Well, we have something called the decision space here. I'm going to go through these different entities one by one so that it starts to become a little more obvious. So when everyone thinks about the word model, they want to see like, well, what is the physical representation of the model here? And the best way I can describe it, again, is it's sort of like a math equation. If we were to take all of our data and take it from the many different columns that we saw before and crush it down into 2 dimensions. Now these axes won't be sort of human readable dimensions or compounded forms of that, but what that enables us to do is actually see the decision boundary from our model and to then look at the decision areas. So for example here, the model will be represented sort of by this purple line on each of these 5 different graphs. In this example over here, we have the same set of data that was fed into 5 different algorithms to showcase how the differences between the algorithms will dictate how the behavior will ultimately be different, despite the fact that they may have very similar accuracy scores on our training data set. What we care about here is exactly how it differentiates between our different classes. So even if the accuracies are similar, we want to see, in what conditions will an algorithm classify a new piece of data as maybe a cheater or an abuser, and in what cases will they classify the user as a non-cheater or a non-abuser. Again, the pros and cons to each of these respective algorithms may lean more towards one scenario or another, or be more applicable for your use case. But largely, we can see here that if you were to take any sort of live data point, which again will have the same headers and columns as any of the data that you trained on, it will fall somewhere on this two-dimensional decision plane, again being compressed down from those n-dimensional vectors. And so where it falls here on the graph, if it either falls in the blue area or the red area for a given model, that will determine whether which class it's being classified as. So we can see here, we want to think about, okay, well, from my training set, if I were to take hypothetical new data points and fill them in here, are there any training data points that are not represented, or are there any data points or trends that are not represented in my training data set? Further, if things were to be changed and new hypothetical sort of data points were possible, would my algorithm in its current sort of state be able to accurately classify those new players? And these are sort of open-ended questions. Depending on sort of the severity of what your resolution is for this inference, it may not be important to have these sort of future questions figured out right away, but the more you automate this process, the more you're going to want to be able to automate your data augmentation steps and your checks for new rollouts. Okay, so that was a lot about sort of machine learning theory and how it's going to apply to today's use case. But I figured we could actually get down to brass tacks and start talking about how we're going to build that pipeline. Machine learning is something that's typically very difficult and requires a lot of theory. I hope I was able to make it a bit more straightforward there. But with services like Amazon SageMaker, you'll be able to see that if you can leverage SDKs and your languages of choice, you'll actually be able to access the benefits of training and deploying of a model to perform inference without needing to mess around with the bit flips and a lot of the underlying machine learning operations that need to happen to make this possible. Okay, so to actually build a pipeline, there are a few core tasks we're going to need here, both on the training side as well as on the inference side. Let's go through sort of the systems design exercise here. First, we're going to have data ingestion. Our data is going to be produced somewhere, typically on our game servers or directly from the client, and we need to be able to ingest that to be used elsewhere. We don't want to tax our game servers more with performing any of this processing directly on those devices, as that can have a lot of different downstream consequences and side effects that wouldn't be fun. Next, we have ETL. From the point in which this data is sort of ingested, we're often going to need to perform pre-processing steps, data augmentation, removal of missing data points, transformation for data types. For example, if the data on the server is stored as a string, but it needs to be in a double or a single numerical, the ETL step is where this will be occurring, and loading the data into the form of compute for the model training task. It's a discrete job by which we feed our processed data, as we talked about before, into a machine learning algorithm to perform our training. This model training typically happens on a cluster of GPU powered devices, as that parallelizing property of GPUs enables us to perform the training at a much greater speed and rate. And again, as the output of that model training process, we're going to have a discrete model file, which we can then build a sort of inference infrastructure around. So this is sort of the disjointing between the two sections. Then we're going to want to be able to deploy the model and create the serving, the inference serving by which we can feed in new live data and perform those inferences as we want. And ultimately, based on the result of those inferences, we're going to want to take actions, either surfacing this data to someone else, or surfacing it to account managers, or automating actions like banning a player if they have an inference that they are definitively cheating to a high confidence value. So part one, implementing this training architecture from a systems design perspective. I mentioned before that you likely have your authoritative game server running on maybe a virtual server like EC2. Maybe you're using a more managed service like gamedev. Or maybe you're using data directly from clients or on some sort of containerized system up in the cloud. Regardless, we're going to want to offload this data to another data store so that we're not performing our computational tasks directly on the game server. Again, our lifecycle management policies for the data that we want to use may be very different from the actual game state and the sessions that persist for our players. So we start with our data on EC2 or gamedev or so on. We then want to offload this directly to a file object store. Something like Amazon S3 works very well because it's entirely serverless It expands to any number of file sizes and any number of files that you may want, and has a lot of really handy event triggers. So you can set things like CloudWatch alarms or CloudWatch events so that when certain events happen, like uploading of a file, you can use that as the trigger for a downstream effect. In this case, performing ETL is going to be something that'll be very valuable here. So for our training, when we have, let's say, a substantial size of files or a number of entries or data points that we've desired in our S3 bucket, we can use that as an event trigger for AWS Glue. It's completely serverless, fully managed ETL service. Essentially, we can write our ETL code directly into Glue and have that kick off as a Glue job. We don't have to provision any infrastructure for that Glue job to run on. Again, being fully serverless, it will do this automatically for us. Once this data and once this data is prepared, ETL has been performed, what we're going to want to do is be able to load this data into a SageMaker training cluster. I mentioned before that parallelizing this with the GPU cluster is something that's very enticing because it increases the speed by which our training occurs. And that's exactly what we're going to do here. Now, traditionally, having to manage the ops around a GPU cluster, even if you're using virtual servers, can become very cumbersome. There's a large number of different machine learning frameworks, and messing around with those drivers is not something that is very fun. Thankfully, SageMaker makes this very easy. Actually, here on the slide, you'll be able to see that with one method call here to sagemaker.fit with a very basic configuration, we can actually automatically have SageMaker take this data, load it, or rather provision all of the infrastructure necessary, load our data and distribute it amongst the master and all of the nodes on this cluster, have it perform that training job, consolidate the results, checkpoint as applicable all along the way, tear down our infrastructure, and then tell us when it's finished performing our training job. And you're only charged for the exact number of clock cycles in seconds for all of the instances that were used. So again, another fear folks have around using GPU instances because they're expensive is that they may be left on for too long. Well, with SageMaker, during your training job, as soon as it's done, all of the infrastructure is spun down. And the same occurs if an error happens midway through, so you don't have to worry about racking up a big bill. So once we have this training cluster, it's performed our training job, it spits out this model file. Again, think of it like an equation. Well, again, this isn't quite actionable yet, so we need to be able to deploy this, much like a lot of software. So thankfully with SageMaker, because it has sort of the context around the software environment that it performed the training in and the libraries that were required for that, if you use those built-in libraries, it becomes very easy to deploy this in one line of code. So by passing in the identifier for the unique model training that was performed, you can use SageMaker.deploy with just a handful of parameters to denote a little bit about the architecture you'll want that endpoint to live on. For example, here being the type of instance or the number of instances in that inference cluster. And just like that, after training with one line of code, you can actually have a deployed endpoint that you can query to perform live inference on. And so this is sort of the end-to-end implementation for a training system for machine learning. Now, when we perform inference, despite the fact that we have our deployed endpoint, we may want a slightly different pathway that may run sort of in parallel to our training. Once we've already deployed our first model, we need to think, well, in addition to retrainings that we may want to be doing, we may have sort of a different lane that we want our data to take to be fed into sort of performing inferences for escalation or for automating actions. So here we can see we're going to start off with a very familiar start. EC2, GameLift, whatever our source of our game data comes from, this is going to be likely the same here as it was before. So players are playing your game. You don't have this labeled data because it hasn't already been studied and labeled by your moderators or existed historically. So we have this live game data. This may be piped out directly to S3 for persisting it, separate from our game sessions. Now, instead of Glue, where we may be performing this larger batch ETL on a large subset of a large batch of our data in preparation for training, instead what we want to do is we want to say, okay, well, as soon as this new piece of data has been fed in, we want to perform an inference and see whether this particular action or set of actions for a player or players in this game were cheating or not cheating. These event triggers in S3 work very well with Lambda as well as with Glue, and Lambda may just be a better fit for this here when we're trying to perform individual inferences. So within that Lambda, we can pass in the context and the event handler for that serverless function. Again, Lambda being fully serverless cloud functions with a pay per processing second model with a very generous free tier up to, I believe, 1 million requests per month. And this fits our sort of situation very well, because as long as the process runs within 15 minutes and the individual model is, again, not loaded into the Lambda's memory, it can become very cost effective and easy to run, operate, and scale out these Lambdas for any arbitrary number of requests, again, being fully serverless. So we actually are going to have this Lambda call out to our SageMaker deployed endpoint. Again, this is what we mentioned before as the artifact at the as the service at the end of training. We can front this with something like Amazon Augmented AI if we want to sort of incorporate from the get-go a human-in-the-loop element to this in an automated fashion as much as possible. But going from 0 to 1, this may not be something that's necessary. And lastly, as a result of that SageMaker deployed endpoint, sort of the world is your oyster as a game developer. Depending on the inference that's returned there to the Lambda function, you can then escalate as applicable or not at all. You could simply save all of this data and then take a look at it in batch all at one time. You can have this conditionally sort of elevated or escalated to case managers, or if it's very confident and you believe in this model, you could have it automate the decision-making process for banning or taking action against players. So now what does this look like with inference when we have humans in the loop? Well, again, we have Amazon Augmented AI here to be able to take in the results of those inferences and conditionally route them either to another moderator or to feed those back into our training scenarios so that we can ensure that our training data for the next version of our model will be more comprehensive. Our model will see the largest gains in its ability to accurately predict outcomes when we're feeding it in sort of these edge cases that otherwise have lower confidence values. And lastly, when it comes to inference, everyone wants things quicker, obviously, but there are trade-offs here. We really see the cost-speed trade-off here and the sensitivity of an organization as the biggest sort of lever. You can, in real time, maybe round by round or in full real time, serve these predictions, but obviously that blows up the quantity and the cost of being able to perform that. Now, semi-real time oftentimes will be more than sufficient. So like at the end of every match, if you have discrete sessions, that could be more than enough. Or you can entirely sort of do this in batch and save the most money. Again, obviously with the longest sort of round trip time on these requests from when the events happen. Think about doing this at the end of every day, at the end of every week, maybe even every month or patch cycle. But again, depending on the cost sensitivity and the demand for having this, the result of these inferences, you have options for how you can be able to choose and break out exactly what use case is best for your organization. Now here we have the evolving architecture sort of next step section. Going 0 to 1 is wonderful, and I've hinted at things like with Amazon Augmented AI, but there are lots of things you may want to consider when automating this even further. First being continuous integration and deployment. This is something that we know very well from the software world, and machine learning in this way it benefits from this as well. You can have triggers based on metrics for automating retraining. For example, if the number of false positives or positive inferences spikes suddenly, you could have this trigger a retraining. You could have this automated in sort of like a dovetail fashion with your patch cycle, so that every time you patch, it automatically retrains as well. And even short of that automated deployment, having canary deployments so that you can actually get a taste for what the inferences are going to look like on live data helps to prevent you from rolling out a new patch that could accidentally break your assumptions about your model, and avoid taking these aggressive actions too early. So lots of options for both building out sort of a more resilient deployment infrastructure from having your model not go haywire, but also to just remove what would otherwise be done very manually. So when it comes to improving prediction quality, this is something that everyone is going to want to do in the long term. You can do everything from tuning your model with different architectures and the infinite game of hyperparameter optimization. Again, think back to the toaster that has a bunch of knobs that you can tune to get your perfect toast, except in this case, it's a machine learning model. Additionally, you can do things like ensemble models where various different endpoints or a single endpoint with multiple models under the hood all feed together to grant a decision. This often increases the robustness of your decision-making pipeline and makes it less susceptible to changes that may catch one model off guard, but may not to the large group in conjunction. Additionally, increasing the size of your training data will help, especially for an imbalanced class scenario like this, where you're trying to get cheaters. These often constitute a much smaller proportion of the player base, where you don't have 50% cheaters and 50% non-cheaters in your data set. And this is a hard statistical problem to solve. So if you can find more of these data points, it's often going to help improve the accuracy of your model in the long run. Next up, data labeling systems. I mentioned that we need data labeling and we need it sort of at scale. And so these systems often don't exist, so we may have to build them to improve this going forward. It may be possible to curate and label a data set to sort of seed this, seed your machine learning ventures, but over time, if you want to really get enough data or a lot of data, a data labeling system may be the way to go. Naturally, players already want to be able to help in this effort, and even if you don't leverage players, you do have, for further labeling, you do have prior data from players, even if you don't think about it. Reports that players have escalated to you, with the outcomes of those reports are already sort of the data set that you will want to leverage for whether behavior that a player was exhibiting was fraudulent or non-fraudulent, or cheating or not cheating, for example. But essentially, if you want to scale this out in the long run, you can build entirely new systems. Now, I know that Valve Software has done this for Counter-Strike Global Offensive with a system they've called Overwatch. But essentially, this is a way by which you can scale out the pairing of behaviors with the labeling of whether that behavior is of a class or not of a class, or of class fraudulent versus class not fraudulent. This will be necessary over time to be able to make sure that one person sitting at a desk isn't labeling your data all day. Additionally, we have a service that helps with this called SageMaker Ground Truth, by which you can pass in a set of unlabeled training data and delegate that to a training workforce, or a workforce that will label this data set. So there are many options there. If you have completely non-sensitive data, you can actually use Mechanical Turk as one of the underlying workforces here. You can also take the other approach where you designate a specific allotment of email addresses from folks at your company or trusted individuals. And then in the middle, you can have sort of like your players. You could have a workforce of approved players that have a certain behavior score or fit certain criteria, and by which you can delegate tasks to them, or SageMaker Ground Truth will delegate those tasks to them. And with the labeling job that you create that looks a little bit like this, you can actually have an example by which you give all of the instructions and all of the necessary data that they'll need, and they can return through this very easy to use GUI the result that you care about for actually providing labeled training data to your model going forward. An example architecture of this sort of data labeling system could look like this, and again, this is very generalizable. Up in the top left, we start with sort of your custom web template. This is the interface by which your labelers will actually interact with. Then you're going to have sort of this task that's going to take the live data. So think of like report cases as they've come in, and delegate those to SageMaker Ground Truth as data part, or like individual data entities that will live within this, or tasks within the overall labeling job. Then those pieces of those labeling jobs will be delegated to the workforce that you've assigned. They'll obviously exist within the manifest in the S3 bucket, and that's where the data is going to live, and that's also where the results will live from the data labeling jobs. And then lastly, after that sort of label is handed down, you may want to have a Lambda function or arbitrary compute that can handle labeling that data and putting that into another data reserve that will be used for retraining your model directly. So again, very simple, very generalizable, regardless of what game type you are working with here, this will work for you. So in short, we talked a little bit about machine learning, well, quite a lot of it. If there's anything that I want you to walk away from today's talk knowing, it's that first, machine learning is going to get around a lot of the pitfalls of arbitrary policy definition and brittleness that exists in that way. Further, you may actually be able to be more accurate and more granular than you'd ever be able to be in a manually designed system for content curation. Further, when it comes to machine learning with human labels, you can actually differentiate and start to interpret things like intent, even if it's difficult to do completely on the merits of the data itself. This is where that subjectivity of using the human labels to train the data set come into play. Things like griefing and things like hacking and abusing can actually be differentiated based on these labels. So thank you for tuning in. My name is Nick Walsh again, developer advocate here at Amazon Web Services. If you'd like to talk to me on Twitter, my handle is over there. But before I go, 3 really quick things. First, please explore the other talks and demos in today's event. There are quite a few of them, and if you found this one exciting, I know you'll enjoy the other ones as well. Next up, if you have additional questions, please stop by the Ask the Experts section, where folks just like me and some of the other presenters will be hanging out to answer any questions you may have. And lastly, for more details on today's session on machine learning and building a pipeline using Amazon SageMaker, check out the Resource Center, where I'll have a lot of different links in addition to the ones that were provided during today's talk. Thank you so much and enjoy the rest of the event.